Hello, everyone. Sorry for the delay. Today I'm going to be talking about truly scalable operational data layers for data pipelines. My name is Matthew Pinarosa. I'm a principal solution engineer at PingCap. I am based in Austin, Texas, and it's my job to solution technical challenges for some of TidyB's largest customers, especially just solutioning at scale. From Hawaii, and a fun fact, I used to be a pro Dota player and streamer. All right. So this session explores operational data layers, which are the global source of truth of aggregated data from internal and external systems. So why do ODLs matter? Most large businesses already have one. Probably most of the businesses you guys are from in this room probably have an ODL in one way or another. And the reason why this is so important in your architecture is it's really nice if users have one source that they can go to get the information that they need. And by having that one source, it creates a lot of, it cleans up a lot of operational challenges that companies face, particularly at scale. So what you'll learn today, we'll talk about what is an operational data layer. We'll break down the concept of scalability, and we'll talk about how to scale to handle diverse workloads. Okay. So this is what a operational data layer might look like in your pipeline. On the left-hand side over here, we have your data sources, which could be your CRMs, your ERPs, your social marketing, ticketing, and from there you're streaming, maybe using Stream Native to get them into your ETL tool, whatever you're planning to use, and from there it'll be ingested into your operational data layer. And right here, your operational data layer can potentially be another database or a combination of databases. I think probably for most people here, it is a combination of databases, but that produces a lot of challenges. The reason why I put TidyB here, is TidyB fulfills a lot of the roles that you need from your ODL. For example, like horizontal scalability, high availability, SQL support, columnar storage support, relational storage support, as well as JSON storage support, as well as resource controls. Multi-tenancy support is key when you're dealing with ODLs because you're dealing with a lot of different consumers. You're dealing with a lot of different applications, all accessing your online data layer. And if you have one system that is putting a strain and causing a noisy neighbor problem, that's just going to be undesirable for this system at large. And it's also strongly consistent. You want your ODL, depending on your application needs, you want your ODL to be strongly consistent. And then finally, when you have your ODL, you can have your data consumers all consuming a single source of truth of information. So scalability, when it comes to ODLs, scalability is king. Downstream from scalability, you get flexibility, you get performance, you get reliability, and you get operability. To quote our CEO, Max, our CEO of TidyB, the fundamental principle of scalability is the ability to expand from zero to many without any design changes. Now, the North Star of scalability, possible or not, should be that any scaling event would sacrifice only one thing: cost. Now, unfortunately, that's not really too much of a realistic scenario. And I think the slide got messed up a little bit here. But when you scale up and you add more users and more tenants, you're collecting more data. You add more data sources. You add new features. That results in more connections, more requests, more metadata to handle, more data to store, more data to scan, more data to process, more data to reorganize, more data to move. And so it's a compounding problem, scalability is. So probably most of the databases that you're using in this room at your companies probably have this problem. As the amount of data, amount of nodes in the system goes up, the duration of your queries, how long it takes to fulfill your queries, goes up. As your quantity of data goes up, your performance starts to cap off, and then you start to need more and more and more hardware to handle the same amount of scale. Now, the North Star of scalability, whether it's possible or not, is that your query latency, your ad index duration, your disaster recovery time, your shard failover time is flat as you scale. When your throughput and your tenancy is linear. So it's as simple as you can get as much performance from 5 nodes as you could get from 100. That's an ideal state. Now, comparing scalability, and these are kind of just popular SQL compatible databases. We can take a look here, and we can take a look at like Aurora. So Aurora is a single write database, and so it's going to be really strong on the stability of latency and then the number of objects. And we also have Cockroach here, which is also a distributed database. And that Cockroach is going to be pretty good on the scale front. It's going to be a well-rounded database with its particular strength being in geo distribution. And then TidyB is going to be great in a lot of more different categories because it separates storage and compute. And it's particularly designed for large-scale scalability, particularly when it comes to throughput and DDL processing. Now, there are a variety of solutions to scale an ODL database. You can do the old school route. You can do database sharding. You can go the NoSQL route. You can do primary-secondary replication, or you can do read-write separation, which is what Aurora does. But there's typically a better way. And that better way is distributed SQL. So distributed SQL is the scalability and reliability of NoSQL with the same functionality of relational databases. You can think of distributed SQL as ACID at scale. On the left-hand side over here, we have our relational databases. And you have your MySQL, you have your Postgres over here. And these databases they have ACID-compliant transactions. They have full SQL support. They guarantee data integrity. But the problem when you scale these databases out is you get complexity. You get massive complexity when you start to scale these databases out to the 100 terabyte range. And then on the right-hand side over here, we have your NoSQL databases, which includes your HBase and your Cassandra. And these databases are actually invented particularly to solve the problem of scalability. And they provide it. You know, the higher scalability, flexible schemas, higher resiliency. But the problem is they have limited query capabilities. You know, if you want to use Mongo, if your finance person wants to use Mongo, they got to learn JavaScript, you know? And actually, I would also add probably operational complexity to the NoSQL side of things, because if you've ever managed a few hundred terabyte HBase cluster, you're not going to have a good time. All right, so how is TidyB suited for operational data stores? Number one, scalability. Scaling out TidyB is as simple as adding another node. And it's also pretty close to purely linearly scaling. Pretty close. It's also highly available. There is built-in redundancy to every aspect of the system. It's also strongly consistent. It also supports advanced query processing capabilities. It's actually the only database in the world that scales as much as it does that supports both transactional and analytical processing. Worry-free schema migration. When you're adding in another data source to your application or to your data pipeline, you need to be able to do schema migrations to change the structure of your data. And so online schema migrations are very important. And as well as workload isolation and resource management. TidyB is specifically built for multi-tenant capabilities. And so you can isolate and designate what percentage of the system should be used by each individual workload. All right, so this is what TidyB's architecture looks like. We have a distributed storage layer, which is our tangibly nodes over here. And this distributed storage layer supports auto and transparent data sharding. And then we have our stateless SQL layer, which is our TidyB nodes in the red over here. And they support your SQL processing and your distributed computing. And we have our cluster management nodes. And these cluster management nodes, these PD nodes, handle data placement, data safety, and workload balance. And every single aspect of this system is designed for scalability and high availability. We scale both reads and writes, and we even have auto-healing capabilities here. If you lose an availability zone, the PD node will schedule to create new replicas in the event of a disaster. Data is also auto-sharded. We map SQL data to key value data underneath the hood. And we split this data into small chunks and regions that are 96 megabytes by default. And we spread these out across different availability zones. And each region has multiple replicas that acts as a consensus group to maintain consistency, even at scale. So this is, I think, the desired state of a truly scalable database system, is that when you scale, all you need to do is add in more nodes. And to put this into practice, for example, LinkedIn, when they were evaluating tangibly, actually evaluated us specifically for linear scalability. And so you can see here, LinkedIn tested us with over 2 million read operations per second with over 30 tangibly nodes. It was actually not that much, to be perfectly honest. And you can see we're almost perfectly, well, not almost perfectly, but like right around the linear scalability mark that we talked about in North Star of scalability. So typical acceptance levels for ODL workloads. ODL workloads require fresh data. If your data is not fresh on your operational data layer, then what's the point? Latency has to be strong. Single query data size doesn't have to be too big, but it has to be reasonable. Stored data size is going to be really important because you need to aggregate data from a lot of different independent systems. Same thing with throughput. ACID transactions are also going to be generally really important, but I think there might be some application scenarios where it might not be. Query complexity, you need to have a reasonable amount of query complexity support. You're going to have to enforce schema, because if you don't enforce schema and you have, you're importing a bunch of NoSQL data, and there's 10 different ways to write revenue, then you're not going to get accurate data. And you also need to have schema flexibility, because if you're adding in, you're scaling, then you need to be able to make changes to your schema without actually incurring downtime. All right, so ODL suitability by databases. On the far right over here, we have Snowflake, and I mean, Snowflake is going to be king when it comes to your single query data size, your stored data size, and your throughput, but it's not really going to be super well suited for your live applications that require heavy transactional workloads. Then we have Mongo, which is also relatively well balanced, but it's going to struggle in the ACID transactions capability as well as schema enforcement. And then we technically can do ACID transactions in Mongo, but they are not very good. And then you have Aurora on this far left-hand side over here, which is technically, I mean, at its core, I mean, technically they've kind of done some magic to make it a multi-node system. I know technically they have a distributed storage layer, but for all intents and purposes, it's a single writer system. And because of that, it's really going to struggle on the scale aspect of things, particularly when it comes to data size and throughput. But it's going to be exceptionally fast because systems that don't have to communicate with other nodes before fulfilling a transaction are actually going to be pretty quick. And then you have tangibly over here, which kind of is a general great fit for all of the different aspects of an ODL. So what does distributed SQL look like in the real world? So Flipkart is the largest e-commerce in India. If you're not familiar with them, they're essentially the Amazon of India, and they run a lot of their workloads run on tangibly. And they've actually done tests on us, and they're able to do 1 million consistent reads per second at 7 milliseconds P99, and 123,000 writes per second at 13 milliseconds P99. And also just because of the way that we store the data, there is a massive compression benefit from moving over from a MySQL or a Postgres. You know, for example, here they reduced their data footprint by 82%. This is another example of an ODL in the real world. So this is from Catalyst. So Catalyst is a SaaS customer success platform. And before tangibly, they were on Elasticsearch and Postgres, and they had a lot of the problems that we've been talking about here. They had issues with query performance and data volume. Elasticsearch lacks joins, which is difficult for doing advanced analytics. DDL is also hard, and the cost is very, very high. And they actually migrated all these independent systems into just tangibly, and with this, they were able to simplify their architecture as well as their operational overhead. And they were able to gain about a 10 times faster latency compared to their previous architecture. Okay. And with that, any questions? Looks like I'm good. Thank you, everyone.
We want to thank our speaker.
Yes.